Confidence intervals for sample proportions. So, what is a confidence interval? Well, a confidence interval is a range of values calculated so that there's a specified probability that the population parameter lies within the interval. Okay. We introduced this in a previous video, but the idea is that we will take a sample, okay, which would be maybe 56%, and then we will add or subtract a value so that we get a range of values. Like in this case, taking 56 plus 4% would give us 60%, and 56 minus 4% would give us 52%. Okay, and that interval between 52 and 60% would be a confidence interval. And that allows us to make a prediction about a population parameter. We would assume that the population parameter is probably inside that interval, and we'll even attach a probability to that being true. Okay. The general form for all confidence intervals, no matter what topic we're covering, is we will take a statistic, and then we will add or subtract what's called the margin of error. Okay. So the statistic could be a sample mean, it could be a sample proportion, it could be a slope. We're going to get to that later. So that is our, remember the statistic comes from a sample. And the margin of error, we get that from a couple places. Okay. The margin of error comes from the product of the critical value times what we call the standard error. Okay. So what I'm talking about now is, where did this 4% come from? Okay, that 4% is called the margin of error, and it comes from the product of the critical value and the standard error. Now, the critical value is some kind of standardized score. For instance, for proportions, and what we're studying right now, that score is going to be a z-score. But later on, when we do this for sample means, we're going to learn about a different kind of standardized score called a t-score. So in general, that standardized z-score or t-score will be called the critical value. And then the standard error is just a fancy way to say the standard deviation of sample statistics. Okay. So it's a type of standard deviation, but it's based on a sample of data. Okay. Not a parameter of data, not a population number. And then remember, the statistic for our purposes right now could be a p-hat or an x-bar. We're going to be studying proportions in this unit, so we'll be looking at p-hats. But in general, that part of the equation is the statistic. Okay. Now, the standard deviation of a sampling distribution we have studied in the past. And this is the symbol for the standard deviation of a sampling distribution. And remember, we used p times 1 minus p over n, and then we took the square root. Okay? And that gave us the standard deviation of the sampling distribution of sizes n, okay, of all samples of size n. Now, this is very related to the standard error of a sampling distribution, which we use when we calculate a standard, we use a confidence interval. Now, the standard error, you'll notice, has almost exactly the same equation, except instead of p and 1 minus p, we use p-hat and 1 minus p-hat. Okay? Think of it this way. Remember, in a real-life situation, we're going to have a population, and we want to estimate some parameter p, so we take a sample, and we calculate a p-hat. All right? We don't know what p is. That's what we're trying to figure out. So there's no way we could use this equation up here because we don't know what p is. When we were studying sampling distributions, we assumed we knew p for the purposes of that unit. But most of the time, we don't know what p is. We're trying to estimate p with our confidence interval. So we can't use p since we don't know it. Our next best guess at the value of p would be p-hat. Okay? So instead of using p, we use p-hat. And when we do that, when we replace that p with p-hat, that is now called the standard error of the sampling distribution. okay, is no longer the standard deviation of the sampling distribution. And it's kind of a terminology thing, but you need to realize that because we're estimating p, we are estimating that sampling distribution, okay? And our best guess for p is p hat. So this is what becomes the standard error in our confidence interval equation. Okay, so this would be the equation for a confidence interval for proportions. Okay, and remember, the equation was statistic plus or minus margin of error. And the margin of error was made up of two things. It was a z-score, or a critical value, and a standard error. Okay, and then because we're doing proportions, the statistic is a p hat. So all I really need to know is what was my sample size and what value did I get for the p hat. Okay. Now, the part we haven't talked about yet is the critical value. Okay. And for proportions, that critical value will be a z-score. And put a star there because that means it's supposed to remind you that this is called a critical value. So a z-score that corresponds to a specified level of confidence is the critical value. And in statistics, we often find one of these three levels of confidence, either 90%, 95, or 99. In theory, we could find any level of confidence we want, but those are the three main ones, and those are the three we'll be using most often in class. Okay, so it's finding the z-score for these is what lets us fill in that part of the equation. Okay, and that'll be our first step in the process. So let's start with a 90% confidence level. We'll start with that with this first picture here. Now, a 90% confidence level, for that, we put 90% in the middle of a normal distribution. Okay, so it's perfectly centered around the mean, whatever that is. Okay, and the critical value for that 90% would be the z-score of either position. Okay, they'll be the same number, but this z-score will be negative, and the one on the right will be positive. And we just use the absolute value of the z-score. Okay, so I need to look up one of those two z-scores. And kind of the easy way to do this is to think about what would be left in the tail of this distribution. And if there's 90% in the middle, that leaves us with 5% in each tail. Okay, so that's the single tail area, 5%. So basically you just figure out what is left. So like 100 minus 90, and then take that divided by 2, and that is the single tail area. Okay. Now I can look up that single tail using a command from our past, which is inverse normal. So if you inverse normal 5%, you get the critical value. Now, if you inverse normal 5%, you get negative 1.645. And if you inverse normal 95%, which would be this position over here, you get positive 1.645. And all we care about is the absolute value. So our critical value for that would be 1.645. You know, the fact that one of them is positive and one of them is negative, that will be taken care of by the equation. Because if you remember, the equation is p hat plus or minus that z-score, and then the standard error. So we're already going to be taking into account that it's positive and negative. Okay, so all we need to do is find the absolute value of that z-score. Now I can do the same thing for 95 and 99. We'd use the same technique. We put 95% in the middle, which would leave us with 2.5% on each side. So the single tail area would be 2.5%. And then when I look that up, which I'll look up as inverse normal 0.025, I get 1.96. Now, recall, we had that empirical rule way back in Unit 1 where we knew that 68, 95, 99.7 rule, remember that? And this was plus or minus 1 standard deviation, plus or minus 2, and plus or minus 3. Well, that plus or minus 2 for 95%, was just a rule of thumb. The actual number of standard deviations for 95% is 1.96. Okay, so we in the empirical rule we said it was 2, which was just 1.96 rounded. Okay, and then for the third one, 99%, that means 99% is in the middle, leaving us with 0.5% on each side. Okay, so that's my single tail area, 0.5%. And when I do inverse normal for that, and this one I actually have to do on my calculator. Remember, inverse norm is in the same place as normal CDF. And I get 2.58. Okay. And again, it would have came out negative 2.58, but I only need the positive version. Okay. This would be positive 2.58. This would be negative 2.58. Okay. So when I want to find a critical value for a certain level of confidence, okay, you always put the level of confidence in the middle of a normal distribution, figure out what is left over on one tail on either side, and then inverse normal that amount. A common thing I see is that someone will say, I want to do a 95% confidence interval. Okay, and then I see them go inverse norm 95%. Well, unfortunately, the answer to that is 1.645. That is the number for a 90% interval. Because when you inverse normal 95%, it's like the 95% started on the left-hand side, leaving us 5% on the right. Okay, so you never inverse normal the confidence level that they ask for. Okay, you always inverse normal what ends up being in one tail, okay, which would be 1 minus 95%, and then divide that by 2. Okay, so it'd be 2.5%, or we'd do 0.025. So that's a very important thing to understand, okay, where we get those from. You are going to get so used to doing the 3 that are listed here that you will, in a day or two, you'll memorize those numbers. And the one we use the most often is the 95% interval. That is the kind of the gold standard. That's the one most people use. So 1.96 is the one that you are going to be using the most often, okay? And remember, that's what goes into the confidence interval equation for Z, okay? Now, let's do an example of how this works, okay? So, suppose we have a jar of blue and orange marbles. That on the right is a jar of orange and blue marbles. That is our population. I want to find the proportion of blue marbles in the jar, okay? I could dump out the whole jar and count all of the marbles, okay? But this is a really big jar, and that would take me a really long time. And we would rather use statistics to figure this out, not just counting, okay? So what I would suggest is that we take a random sample of 50 marbles. So that means that n is 50. And I count, out of those 50, that 16 of them are blue. Okay? So 16 blue marbles out of 50 gives me a p-hat of 32%. Okay? So that's going to be important. That's my sample proportion. Okay? Now, if I took another sample of 50 marbles, I would probably get a different proportion. It might be close to 32%, but remember, because of sampling variability, it probably won't be exactly the same, okay? And we want to get an estimate of the actual proportion of blue marbles just based on this one sample, okay? This 32% is called our point estimate of the proportion of blue marbles. Like if somebody said to you right now, what percentage of marbles in this jar are blue, your best guess would be 32%. Okay, because you took a sample and that's what we got. So we call that the point estimate. Okay. Now let's create a 95% confidence interval for the true proportion of blue marbles in this jar. Okay. Because again, we know even though it's a point estimate, Another sample would give us a different point estimate, okay? So here's how we would construct the interval. I said we want a 95% interval. This is the equation we will use, okay? And I know my p hat was 32%. That's what we got on the previous slide. So let's calculate, like I already have this value, right? P hat. Let's calculate the standard error, which is the stuff in the square root. So that would be the square root of p hat times 1 minus p hat over n. And I know p hat was 32%, so 1 minus p hat would be 68. And I divide by my sample size of 50. Don't forget to take the square root in the end, and I get 7%. Okay, so 7% will be my standard error. So that will go into the equation for here. And the only other thing I need is the z-score. And I wanted 95% confidence. So remember from the previous calculations, for 95% confidence, we use a z of 1.96. So filling in my equation, p hat is 32%. The z-score is 1.96. And my standard error was the 7% from over here. Okay? The plus or minus part of this equation is just a part of every equation. Okay? Remember, that's how we're going to get our interval, by adding or subtracting this margin of error that I'm going to get. So let's calculate the margin of error, and we do that by multiplying these two numbers together. So 1.96 times 0.07 gets me 14%. So this is one way to write a confidence interval, is to say it's 32% plus or minus 14%. Okay, the 32 is our point estimate, remember? And the 14% is our margin of error, which we abbreviate as MO. Okay, that's our margin of error. Now, another way to illustrate this confidence interval would be to actually take 32 plus 14%, which would be 46%, and do 32 minus 14%, which would be 18%. Okay, so this ends up to be my confidence interval, 18 to 46%. And this is called interval notation. We usually put confidence intervals in parentheses, and we separate the values by a comma. Okay. Now, this is our conclusion. Okay, and we'll talk about how to construct this later, but this is what it would sound like. We say we are 95% confident that the true proportion of blue marbles in the jar is between 18 and 46%. Okay, a couple things in here that you have to have. You have to say the level of confidence. Okay, and that's exactly the way you word it, that we're 95% confident. If you want to be 99% confident, we would have used a different number for the z-score. Okay, or if we wanted to be 90% confident, we would have used a different number for the z-score. So it's important to report what level of confidence we used. And then we always make this conclusion in context. So we were trying to find the true proportion of blue marbles in the jar. Okay, like that's what we were trying to find. And then we just state it. It's in between 18 and 46%. So that would be a perfect conclusion on the AP exam. Okay. Now, interpreting a confidence interval. This is what, these two statements are very important. Okay. For the interpretation, you want to say this sentence by filling in the blank. We are blank % confident that the true proportion of blank is between blank and blank. So those four things you need to fill in, okay? How confident were you? What proportion were you trying to find, okay? Like, was it the proportion of blue marbles? Was it the proportion of Democrats? Was it the proportion of students who have a job? Like, what were you trying to find? And then just state the two percentages that are the edges of the interval, okay? Now, what does it mean to be 95% confident? This is another thing you need to learn. Okay, like when we say 95% confident, what does that actually mean? Okay, and what it means is this. If we repeated this process many, many times, we would expect, on average, that, like in our case, 95% of our intervals created would contain the true population proportion. Okay, so basically it means if I sampled 50 marbles out of this jar and infinitely many times, okay, like a meta experiment. If I did that and calculated a confidence interval for every sample that I drew, okay? 95% of those intervals would actually contain the true percentage of blue marbles that are in that jar, and 5% wouldn't, okay? So basically, every 100 intervals I create, I would expect 95 of them to actually have the real percentage of blue marbles in it, and I'd expect 5 to not have it in it. Now, will that happen exactly every 100 times? No, okay? Remember, this is a meta experiment. Think of doing millions of these intervals, okay? And at that point, 95% of them would contain the true population proportion, okay? So obviously, if we use, 99% confidence, we would be more sure that we had it, that we had captured the true proportion. And if we use 90% confidence, we would be less sure, okay? But there are some trade-offs with that too, and we'll discuss that. 95% confident, though, is the usual value we're going to use, okay? So these are two statements that you need to memorize, okay? Interpreting a confidence interval, we're something percent confident that the true proportion of blank is between blank and blank. And what does it mean to be 95% confident? It means if you repeat this process many, many times, we'd expect on average that percentage of our intervals created would contain the true population proportion. Okay. On the AP exam, you will most likely be asked one of these two questions, and you will have to write it out. Okay. So you need to be confident in writing these two two phrases. Okay. And we'll practice it a bunch. Now, this is just an example. Okay. I have a computer program that allows me to, let me straighten this out a little, create 100 confidence intervals at one time, okay? So I took a sample of 50 marbles, and I made 95% confidence intervals, and I asked the computer to do it 100 times. All right? Each line on this, each black line represents one interval. So there are 100 lines on this graph, okay? Now, the black intervals indicate that we hit the actual proportion, okay? And the actual proportion is the blue line here. So that's the P, okay? So in this case, it looks like it's somewhere between around a little over 30-something%, okay? The black intervals, if you notice, they all touch that blue line, which is the actual proportion. The red intervals are the ones that missed, okay? So what I mean by that is, if you look, like this interval did not contain the actual proportion. This one did not either. No, no, no. This one's a big no, and this one's a no. So how many missed? So that's 1, 2, 3, 4, 5, 6, 7. So in this sample, 93 out of the 100 intervals were correct. And by correct, I mean they actually contain the true proportion of blue marbles. And 7 out of 100 missed. Okay, you could say these hit it. All right, now we said we were 95% confident. But remember, it doesn't mean that every 100 intervals will exactly have 95 of them that hit it. Okay? That's in the long run that should happen. So sometimes, like in this case, only 93 of them hit. Maybe the next time, 97 of them would hit, etc. Okay? But notice, even the ones that missed were pretty close. Okay? And when you're out in the real world, you'll take your one sample and you'll create your interval, and you don't know which one of these intervals you actually got. Is it one that hit? Is it one that missed? But you can tell from looking at this, more than likely, your confidence interval actually will contain the true proportion. Okay. On this example, I asked the computer the same thing. Choose samples of size 50. Do it 100 times to make 100 intervals. But I asked the computer to only be 90% confident, which means in my equation, instead of using my z-score to be 1.96, I used a z-score of 1.645. Okay. Now, when that happens, I use a smaller z-score. That means my margin of error is going to be smaller. Okay. It means my margin of error is going to be smaller. So my interval will not quite be as wide. So I'm going to miss more often. Okay, and now this time, if you count the misses, there's 1, 2, 3, 8, 9, 10. So I missed 10 times, which is what we would expect, right? We expect 90 out of the 100 intervals to catch the p, the true proportion, and we'd expect 10 out of 100 to miss. So this example actually did exactly what is supposed to happen. We're supposed to miss about 10 times when we use 95 or 90% confidence. If you could compare this one to the previous one, you would notice that the length of these black lines is a little shorter. Okay? So our interval isn't quite as wide, which is why we miss more often. Okay? But the trade-off with that is that if I'm right, I have a little smaller interval. Like I know a little more information. Like instead of it being, plus or minus 14%, maybe it's only plus or minus 10%. So I have a better idea of what the actual proportion is if I'm right. Okay. Here's another example. I did the same thing. I chose a sample size 50 marbles. I did it 100 times. I made 100 confidence intervals. But this time I asked for 99% confidence. So notice my intervals are longer now. Hopefully you can tell that from looking here. This is longer now. Okay, because remember for 99% I use 2.58 as my z-score. So that means my margin of error will be much bigger. So notice this time I only missed twice. Okay, so 98 out of 100 times I found the true p. When I say found the true p, I mean it's in the interval. And 2 out of 100 times I missed the true p. Okay, so when I use 99% confidence, I'm more sure that I've captured the true proportion. But if you look, the interval is so long now that my margin is almost 30% wide. So yeah, I know it's in there, but I haven't really pinpointed it. Okay, and we want, there's a balance between the confidence level, being confident in my answer, but also having a narrow enough range where I truly kind of have an idea of the proportion of blue marbles. And so that's why a really good medium point trade-off is to use 95% confidence. Okay, it's a good balance between the size of the interval. I don't want an interval that's so big versus being really sure it's in there. Okay, so 95% is a good deal. So here's just a quick comparison of the three graphs I just showed you. Okay, and you can see I did these on the same scale, so you can see the smallest confidence intervals were in the 90% picture, and then the 95% ones got a little bigger, and the 99 ones got even bigger yet. Okay, and we missed a ton in the 90. We missed 10 of them. We missed fewer here, and the intervals weren't quite as big. Here we didn't miss as many, but the intervals are so big that it's kind of hard to tell. Okay, and the only difference when you look at those confidence interval formulas, which is one of the reasons I put these all up here, the only difference between these three formulas was the z-score I used. Okay, and that comes from the level of confidence I wanted. Okay, so you take your sample. The sample is the same in all of these. It gives you the same standard error in all of these. The only difference was how confident I want to be in my results. And the higher the confidence level I choose, the more confident I can be. Okay, so that's important to understand. In this case, I want to do another comparison. This time, all of these three confidence intervals are 95% intervals. Okay, so for each one I used 1.96. And I got the same p hat for each one. So the sample was 32 each time. Okay, but what I changed this time was each time I took a bigger sample. So notice in the first graph I took a sample of size 50. Okay, and how many did I miss? I missed 1, 2, 3, 4, 5, 6. I missed 7, so I was 93 out of 100 right. In the next one, I doubled my sample size to 100. Okay. So now, notice this time I missed, let's see, 1, 2, 3, 4, 5, 6. I missed 7 again. Okay, but if you could look carefully, my interval size for the sample size of 100 is a little smaller than the sample of size 50. And you can really see the jump in the next one. I went from a sample size of 100 in this one to a sample size of 250 in the bottom. Look how small these intervals are now. But notice, I only missed 3 times, okay? So I was right 97 out of 100 times there. And notice my intervals are very small, so I can really pinpoint where the percentage of blue marbles is located, okay? So that's another thing we can do to control this, okay, is take a bigger and bigger sample size. The bigger the sample size I take, the more accurate my results are going to be, and the smaller my interval is going to be, okay? So 95% confidence with a decent sample size gives you a really good confidence interval, okay? So in general, the bigger the sample size, the smaller the interval will be. You could say the more accurate it will be. Okay? And the more confidence we want to have in our process, the larger the interval will be. Okay? So, if I want 99% confident, that's going to make a bigger interval so that I'm more sure I'm correct. Okay? And if I'm willing to have less confidence in my answers, I can make a smaller interval. Okay? So those are 2 very important concepts to understand. The bigger the sample size, the smaller the interval will be because it's more accurate. And the more confidence I want, the larger the interval I need to create. Now, there are 5 steps to constructing a confidence interval. And we have a mnemonic memory device here, which we call panic. Okay? And this allows you to do all the necessary steps on the AP exam to get full credit for doing one of these intervals, okay? So, panic. First letter is P, and that stands for population and parameter. On the AP exam, they want you to name the population that you're looking at and the parameter you're searching for. Okay, and that doesn't look like searching, so I'm going to rewrite that, sorry. Okay, so in our marble problem, we'd say the population is the jar of marbles, and the parameter we're searching for is the proportion of blue marbles in the jar. Now, in order to do a confidence interval, we have to know that our sampling distribution is going to be approximately normal, okay, because we're using z-scores. So to do that, we need to check what are called the assumptions or the conditions, okay? And we've done this before in a sample distribution unit, okay? Remember the first condition was we need to make sure we took a simple random sample from our population. The second condition was, remember the 10% rule? So we can't sample more than 10% of the marbles in the jar. And our third one was, if you remember, we wanted to make sure we had at least 10 successes and at least 10 failures. And in the sampling distribution unit, we used n times p bigger than or equal to 10, and n times 1 minus p bigger than or equal to 10. You can probably guess, we don't know p, right? That's what we're trying to figure out. So in confidence intervals, we do n times p hat must be greater than or equal to 10, and n times 1 minus p hat is greater than or equal to 10. It's kind of like the standard error. Since we don't know p, we have to substitute the p's with p hats. So if those 3 conditions are met, and again, it would be just like sampling distributions where we'd need you to spell out why they're true. You can either list off the reasons or you could write a little paragraph, okay? But that needs to be a part of it. And then the third step, N, stands for name the interval. And they want us to name the interval. So we could call this a 1 proportion Z interval. Okay, it's one proportion because we took one sample. Okay, you can bet or probably guess that there'll be a two proportion one maybe later, but it's one proportion, and then we use a z to create the interval, and we call it an interval because it's a confidence interval. That is actually going to be the name that you're going to find on your calculator to do this activity. We call it the same thing. I stands for the interval itself, and on the AP exam, all you need to do is write the interval. Okay? So just use some means of calculation where we're just going to list off the interval and interval notation. On the AP exam, you do not need to show the formula. Okay? That is not required. The only time the formula would be required is if you forgot the name of the interval. Like if you couldn't think of what to write for the name, then you would need to show the formula itself. But the name counts for the formula. Okay? And then the conclusion at the end, this is where you say, we are blank percent confident the true proportion of blank is between blank and blank, which we learned before. Okay? So that would be a complete confidence interval. Name the population and the parameter you're searching for. Check the assumptions so that we be sure we have a normal or approximately normal sampling distribution. Name the interval we're going to create. Give the interval, and then state your conclusion. Okay? That would be full credit on the AP exam if you included those 5 parts. So we kind of joke that anytime you want to make a confidence interval, all you should do is panic. Okay, but you shouldn't really panic. All right, so let's do one of these from start to finish. So it says, a recent Gallup poll conducted telephone interviews with a random sample of adults aged 18 and older. Whoa, so that sounds like the population, adults 18 and over. It said it was a random sample. That's important, right? Data were obtained for 1,000 people. That sounds like my sample size. Of these, 37% said that football is their favorite sport to watch on television. So that 37%, we can guess that's the p hat, right? Then it says, construct and interpret a 95% confidence interval for the true proportion of people whose favorite sport is to watch football. So construct and interpret. So it wants me to make the interval and then tell them what it means, okay? And 95% confident, that's important because that tells us what z-score to use, right? We're going to use 1.96. So when you're doing a problem like this, the first thing we would do, you could write down a capital P, because remember right now we are starting to panic, right? The P stands for population and parameter, so we'd say we are looking for the proportion of adults ages 18 and older whose favorite sport to watch is football. Okay, so that took care of both things. I told you who the population was, because I said we're looking for the proportion of adults ages 18 and older. So I know that my results are going to be talking about adults 18 and older whose favorite sport to watch is football. That's the percentage I'm looking for. So P is taken care of. A is assumptions or conditions. So here's where we need to mention those are 3 conditions, where we say we randomly sampled 1,000 people, which we assume is less than 10% of all adults 18 and over, which I think is a pretty good explanation, okay? And then we would say, 1,000 times 37%, and 1,000 times 63% is 370 and 630, both greater than or equal to 10, okay? And then we can say, therefore, p hat is approximately normal. Okay. Now, n is name the interval. So we'd say, we will create a 1 proportion z interval. Now, I is make the interval itself. So we could fill in all this information if you want. So remember our p hat is 37%, plus or minus the z-score, the critical value, which is 1.96. And then my standard error of the sampling distribution, which would be 37 times 63% over 1,000, and I'm going to take the square root of that. Okay. Now, with a little calculation, I get that it's 37% plus or minus 3%. I'm going to round to the tenths place. So at 3% is the margin of error, which is the 1.96 times the standard error. And then I could take 37 plus 3% and 37 minus 3%, and I would get 34 to 40% be my interval. So that is my I. And again, this part of it, the calculation part, I do not need to show this, okay? I could just write down the interval. But then the last part would be the conclusion, C, where we would say we are 95% confident the true proportion of adults who are 18 and over whose favorite sport is football is between 0.34 and 0.40. Okay, that would be the full correct confidence interval. Okay, so you can see how panic will help us. It really spells out exactly the steps we need. And on many AP exams, kids actually write out the PANIC right on their paper and fill in each step as they go. And this panic isn't something that we came up with at Jefferson. This is something that's used nationwide. Okay. In fact, when the person that corrects your AP exam sees that statement, they know exactly what you're getting at. Okay. All right, so that's our first confidence interval. Yay. Now, I do want to show you how to do this on your calculator. Okay. On your calculator, if you go to Stat, and then when you hit that button on your calculator, you get to the Edit, Calc, and Test screen. Okay. If you arrow over to Test, because this is considered one of the testing procedures. If you go over to tests, you'll get this long list of different tests that you can do. And what we're looking for is letter A, and this is the same on either calculator, the 1 proportion z interval. Okay, and you can see that's what it means, 1 prop z interval. Okay, and then to do this interval, you need to fill out this next screen. And remember, this is all based on p hat. Well, p hat, the equation for that is x over n, where n is the sample size and x is the percent, or the number of people that, or like the number of blue marbles we found, or in this case, it's the number of adults 18 or over in our sample that like to watch football. So on the calculator, though, instead of typing in 0.37, they want us to type in the fraction that got you that, okay? So they want us to type in that they sampled 1,000 people, and 37% of them liked football as their favorite sport. And 37% would be 370 out of 1,000. Okay? So that's how we enter that in our calculator. We actually have to enter in 370 and then 1,000. Okay? If you just typed in the 37% up here, in one of those spots, you'll get an error statement. Okay? So be careful about that. You have to type in that fraction. And then the confidence level, you pick this. We wanted 95% confidence, so you just type in 0.95. If you wanted 90%, you'd type in 0.90. If you wanted 99%, you'd type in 0.99. And then you just hit calculate. And then on the next screen, it gives you the interval. Remember, we said it was 34 to 40%, and you can round those to 2 decimal places. And then it tells you what p-hat was and the sample size. So you can just make sure you did it correctly. But that's how you can get the interval on your calculator. Okay? And from this time on, if you have to do this on a homework assignment, we'd prefer if you just used your calculator. Okay? Run the 1 proportion z interval, type in the p-hat fraction, choose your level of confidence, and get the interval. Okay? So this would be the I part of the panic. Okay? This is how you get it, the I part. There's one more thing you need to know about confidence intervals. Okay? First, let's quickly review some stuff about it. So it says, suppose a 95% confidence interval for the percentage of students who can roll their tongue at Jefferson is found to be 28 to 40%. So the interval is 28 to 40. Rolling your tongue, it's when you try to curl up your tongue on both sides and make a little tunnel. So you have to be able to interpret the confidence interval in context. So we would say we are 95% confident the true proportion of students at Jefferson who can roll their tongue is between 28 and 40%. If we interpreted the confidence level in context, we would say, if we created many confidence intervals using the same technique, we would expect 95 of 100 to contain the true proportion of tongue rollers. Okay, so remember, it's like a meta experiment. If we repeated the process many times and made many intervals, we'd expect that 95 out of 100 of them to contain the true proportion of tongue rollers. I'm going to make this true better so you can read it. Okay. Now, this is interesting. C says, what was the point estimate p-hat from which this confidence interval was constructed? This is a skill you need to have. Remember that the p-hat is right in the middle of the interval. Okay, because remember we do plus or minus the margin of error from that p-hat. So all we have to do is find the middle of our confidence interval, and that's p-hat. So to find the middle, you simply add up the 2 endpoints and divide by 2. So this would be 68 divided by 2, and 68 divided by 2 would be 34%. So in this problem, the p-hat was 34%. So I can find that out by just finding the average of the endpoints. Okay. So that's something you need to know how to do. Okay, finding the point estimate from the interval. Also, what was the margin of error for this confidence interval? So I want to know, what did you add or subtract to 34%? Okay, so remember it'd be 34% plus or minus the mo. So what was the plus or minus? Well, to do that, instead of adding the 2, subtract the 2 and divide it in half. So if I subtract these 2, I get 12%. And 12% divided by 2 is 6%. So the margin of error, the mo, was 6%. So when they made this interval, they did 34% plus or minus 6%. Okay. So you need to know how to do both of those calculations. How do you find the value for the p-hat, the point estimate? And how do you find the margin of error if you have the interval? Okay. You add them up and divide by 2 to find p hat. You subtract the endpoints and divide by 2 to find the margin of error. All right, the last thing we need to talk about is estimating the sample size that we need to take in order to create a certain margin of error, okay, or a certain width of our confidence interval, all right? And many companies do this ahead of time, like Gallup or other places that do polls. They know at the end when they write the article that they want to say, hey, maybe we only want to be off by 3% in our sample, okay? And most places use 95% confidence, so they're locked into a z-score of 1.96. The only thing we can really affect is the size of the sample that we take, okay? So one thing we need to be able to do is solve this margin of error equation for a certain sample size, okay? And what we'll do is that we already know z, they're probably going to give that to us, and it's usually 95%. And as far as what p do we use and 1 minus p do we use, if we have not done, like if we're sampling from a population we know nothing about, we just use 50% as the p hat. We just assume there's a 50-50 chance of whatever we're trying to find. And then of course 1 minus that p would also be 50%. And then we just end up solving this equation for n, the sample size. So let me show you what I mean. So officials in Jacksonville, Florida would like to estimate the percentage of adults who've been in a hurricane, okay? How many residents should be surveyed if they want a 3% margin of error with 90% confidence? So what we know is they want to be able to say at the end of the study, okay, when they make the confidence interval, they want to be able to say p hat plus or minus 3%. Whatever sample they get, whatever sample proportion they get, they want to be able to say it's plus or minus 3%. All right? So what they would do then is take this equation and set it equal to 3%. Okay? I want that margin of error to be 3%. Now, I already know what z-score they're going to use because they're going to use 1.96. And since I don't know what percent of the people have been in a hurricane, what we do is we assume there's a 50-50 chance to start with. Okay? This gives us the best chance to get the right sample sizes to use 50-50. Okay? Sometimes when they do this, they'll say, we did this survey 10 years ago, and we found out that the p hat was 48%. So they might start with 48% and 52% as the p and p hat if they have previous information, okay? But in this case, let's just assume we don't have any previous information. We would go with 50-50. And now we would just solve this equation for the sample size n. And the way we would do that is we would first divide both sides by 1.96, okay, which would leave me with, and I'm going to multiply the 0.5 and the 0.5 together, that's 0.25. And 3% divided by 1.96 would get me 0.0153. Okay, then I would, solving for n, I would have to square both sides to get rid of the square root. So I would square 0.0153. And I get a kind of a crazy decimal. I got 2.34 times 10 to the negative fourth, which means I move the decimal 3 places. So there'll be 3 zeros in here. So 0.000234. And then to finish this, I'd multiply both sides by n. Okay, and then I would divide both sides by the 0.000234. Okay, so I'd do 0.25 divided by 0.000234. And I would get this, n equals 1068.4, And we can't ever sample 0.4 of a person, so the rule is you round to the next whole person. So my n would be 1,069. So this would tell Gallup or whoever's doing the poll that if they want to be able to say at the end of their survey, when they make a confidence interval, if they want to be able to say plus or minus 3% of whatever sample they get, they should send this sample or survey to 1,069 subjects. Okay. This is probably one of the harder things that we end up doing in this chapter, because you have to make this calculation by hand. Okay, and you got to be able to solve for n. But there will be practice in the homework. Okay. Good luck with confidence intervals.